Hey there, data enthusiasts. Welcome back to our channel. If you're passionate about data science, machine learning, or just curious about how algorithms make decisions, you've clicked on the right video. Today, we're diving into a crucial concept in model evaluation, the confusion matrix. So, grab a notebook and let's get started. Now, let me ask you this: have you ever wondered how we can measure the performance of a machine learning model? How do we know if our model is making the right predictions? That's where the confusion matrix comes into play. A confusion matrix is a fantastic tool that helps us visualize the performance of a classification model. It summarizes the results of predictions on a classification problem. Basically, it lays out how well our model is doing in terms of true positives, true negatives, false positives, and false negatives. Let's break these terms down. True positives. These are cases where the model correctly predicts the positive class. For example, if you're predicting whether an email is spam, a true positive would be an email that is indeed spam and the model correctly identifies it as such. True negatives. This refers to cases where the model correctly predicts the negative class. Using the spam example again, a true negative would be a non-spam email that the model correctly identifies as non-spam. False positives. These are cases where the model incorrectly predicts the positive class. In our spam example, a false positive would be a regular email that the model mistakenly identifies as spam. False negatives. This is the opposite of false positives. Here, the model incorrectly predicts the negative class. So, if a spam email is mistakenly classified as non-spam, that would be a false negative. Let's look at a concrete example to see how this works. Imagine you have a model that predicts whether a tumor is malignant or benign. After running tests on a batch of 100 tumors, you get the following results: 50 true positives, 30 true negatives, 15 false positives, and 5 false negatives. When we put this into a confusion matrix, it looks something like this. This matrix gives us a clear visual representation. But how do we extract meaningful insights from it? That's where performance metrics come in. From the confusion matrix, we can calculate various performance metrics, including accuracy, precision, recall, and F1 score. Accuracy. This tells us the overall correctness of the model and is calculated as TP plus TN divided by TP plus TN plus FP plus FN. For our example, that would be 50 plus 30 divided by 100, which equals 0.8 or 80% accuracy. Precision. Precision measures how many of the predicted positives were actually positive. It's calculated as TP divided by TP plus FP. In our case, that's 50 divided by 50 plus 15, which equals 0.769 or about 77%. Recall. Recall tells us how many actual positives were correctly identified. It's calculated as TP divided by TP plus FN. For our model, that would be 50 divided by 50 plus 5, which equals 0.909 or 90.9%. F1 score. The F1 score is the harmonic mean of precision and recall and provides a balance between the two. It's calculated as 2 multiplied by precision times recall divided by precision plus recall. In our case, that's approximately 83.3%. Each of these metrics provides a different lens through which to evaluate our model's performance, and which one to focus on often depends on the specific problem we are tackling. So, to wrap it up, a confusion matrix is an invaluable tool in the world of machine learning, allowing us to visualize and understand our model's performance clearly. Whether you're tracking true positives or calculating precision and recall, mastering this concept can help you build better predictive models. If you found this video helpful, be sure to hit that like button and subscribe for more educational content on data science and machine learning. And if you have any questions or topics you'd like us to cover next, drop a comment below. Thanks for watching, and see you next time.